Hello. So, in this lecture we will talk about rigid body modes of in a multi-degree of freedom system. So, let us get into the concept of rigid body mode. So, as many of us know that a rigid body mode is defined as the free translation or rotation of a body without undergoing internal deformation. So, suppose I have a system of this form and I apply external loads and moments on this system. So, this is a deformable body. So, this is a deformable body. Now, when I apply this forces and moment on a deformable body, the body is going to experience strains and stresses or deformation. The strains and therefore the stresses, and the strains can also be I mean, instead of strain we can also say that this body is going to experience deformation. Now, apart from deformation, the body, though deformable, can actually move or displace, translate or rotate without some internal deformation of the body. So, what is going to happen? This body, when applied these forces M1, F1, F2, M, etc., which are generic forces, it will undergo deformation or strain, as well as it will undergo a pure rigid body kind of deformation without rigid body kind of rotation and translation, which will happen, and this kind of translation and rotation may happen without any internal deformation of the body. So, along with the deformation, along with the internal deformation of the body, there are going to be translation or rotation which will be because of the rigid body displacements or rotation of the body. So, this concept is very well known in our from our basic engineering mechanics. So, we are going to see what is the effect of this kind of rigid body deformation in case of dynamics or in case of vibration. So, let us take this very simple example. So, we have two masses M1 and M2 connected to each other with a spring of spring constant A. So, the mass M1 is having a degree of freedom U1 and the mass M2 is having a degree of freedom U2. Now, let us look carefully into the system. Now, the system can actually vibrate so that the spring gets deformed. Okay. So, there could be a relative motion between M1 and M2, U2 is not going to be equal to U1. So, there is a relative deformation. As a result, the spring is going to get deformed, which is elongated or contracted, okay, deformed or elongated. Okay. This can always happen, this kind of motion can always happen, we are very much aware of that happening. But apart from that, what can happen is that U1 T can be equal to U2T and this whole body can move on its own without any deformation of the spring K. So, the spring K will not be elongated or contracted or compressed. Okay. So, this kind of motion is a rigid body motion. where the spring is not experiencing any deformation and u1 is equal to u2. So, therefore, this whole system of this two mass can have two kind of deformation. One would be a regular vibration because of the oscillation of m1 and m2, and one could be a rigid body motion. So, the rigid body motion is happening because we have not constrained the rigid body translation. So, the rigid body translation is in this direction and we have not constrained it. Had there been a spring here, then there would have been no rigid body mode. There would have been no rigid body mode and we would not have got any rigid body mode, and that would have been a different case. But since there is no constraint, this system of these two masses is free to have a rigid body mode. So, now let us look into the problem in more detail and see what is going to happen if there is a if we have such a system where a rigid body translation or rotation is allowed, or because of the lack of constraint. So, let me first write down draw the free body diagram of the system. Okay. So, the mass m1 has u1 degree of freedom. So, there is a inertial force m1 u1 double dot and then a spring force k u2 minus u1, and for the second mass okay. So, if I write down the equations of motion, I can write it down as m1 u1 double dot plus k1, let me write it as minus k into u2 minus u1 is equal to 0, which in turn can be written as m1 u1 double dot plus similarly. So, this is the first equation of motion. Similarly, the second equation of motion is going to be so, these are my two equations of motion. So, now if I write it in matrix form, okay. So, now let us try to find out the natural frequency. So, Okay. So, these are the two natural frequencies. So, we see that M1 and M2 are arbitrary. I have not assumed any particular value for M1 and M2. So, we have seen that if we solve the characteristic equation and try to find out the natural frequency, we will see that one of the frequency is coming out to be 0 and other is another positive number. Okay. So, see, we have not assumed anything special while we found out the natural frequency about the rigid body mode. We have seen physically that the system that we are considering can physically have a rigid body mode, but while we were doing the mathematical calculation, we didn't assume anything special or anything particular pertaining to the physical understanding of the rigid body condition, possible rigid body motion of the system. So, we have followed the normal process to find out the mass and stiffness matrix and the normal process to find out the natural frequencies. And we have found out that one of the natural frequency is equal to 0. Therefore, we can say that if a system has one or more rigid body modes, then the natural frequencies are going to be equal to 0, or in another word, the number of rigid body modes in a system, so in this particular case, we had only one rigid body mode. There could be systems where we can have more than one rigid body mode. This is equal to number of 0 natural frequencies of the system. So, if I have a system with 3 rigid body modes, we are going to see that 3 of the natural frequencies that we determine are going to be 0. Suppose I have a 10 degree of freedom system and out of which there are 3 rigid body modes, therefore, there would be 10 frequencies or 10 values of omega that we can evaluate. Out of this 10 values of omega, there would be 3 0 values of omega. Or in a reverse way, we can say if we find out that certain number of natural frequencies are 0, from the suppose we get the mass and stiffness matrix and we straight away find out the natural frequencies even without looking into the system, and we find out that certain number of natural frequencies are 0, then we can say that this many number of rigid body modes are present in the system. So, this many number of rigid body modes or translation and rotations are unconstrained in the system. So, that is why in the earlier part of the lectures on multi-degree of freedom system, I said that the stiffness and mass matrix are always positive semi-definite. Positive definite when that is that eigenvalues are always greater than 0 when there is no rigid body mode, and equal to 0 when some of the rigid body modes are present in the system. So, if we get any system and we see that there are certain number of 0 natural frequency, then there are that many number of rigid body mode, and we may or may not like to constrain, if possible we would like to constrain those rigid body mode if we have a control on designing the system. or in some system we cannot avoid the rigid body modes. For example, if we have a flying aircraft, we cannot constrain certain rigid body modes of the aircraft. So, there would be, if we do a complete analysis of the whole aircraft and trying to find out the natural frequencies, the several natural frequencies of the whole aircraft, there would be several natural frequencies which are going to be 0, because we cannot make the aircraft free from any rigid body modes. So, with this we are going to move on to a new topic on the numerical time integration. So, all this while we have been talking about analytically solving a problem, a vibration problem or a structural dynamics problem. So, all this while, all the method that we have talked about is about solving the problem using a pen and paper and a calculator at most. Now, this kind of techniques are called analytical techniques, as most of you all might be knowing. So, we are not using any numerical tools to solve the problem. So, there are several advantages of an analytical scheme, because analytical schemes helps us to physically understand the system. Suppose I have a 10 degree of freedom system. If I do modal analysis, I will of course be able to know what are the mode shapes, what are the natural frequencies, what are the resonance frequencies. The natural frequencies are going to be the resonance frequencies. So, we have to avoid those frequencies. We know that how, if we depending on the damping, how would be the magnification factor for each of these natural frequencies when there is a harmonic loading. So, all this physical understanding is very well appreciated when we do a mathematical model or an analytical model. So, whenever we try to solve a problem, all of us, even in industry, people first try to simplify the problem into a smaller problem and try to solve it analytically using the techniques like modal analysis, using the convolution integral, using harmonic loading, magnification factor, so as to get an overall idea about the physics of the problem. So, once the physics of the problem is understood through this numerical problem, then usually people do a large scale analysis. So, suppose we are modeling, since we had ended the last talk with an aircraft, example of an aircraft, suppose we are trying to analyze the vibration of a whole aircraft. So, the number of degrees of freedom of a complete aircraft is numerous. It could be 100, 200, and it is actually not possible to do a complete pen and paper analysis of the 100 degree of freedom system. So, there comes the numerical techniques. So, one common numerical technique that most of us use both in industry and in academia to solve large problem is the finite element method. So, if I take a whole full scale aircraft and if I do a finite element analysis, I will get a stiffness matrix for the aircraft, I will get a mass matrix, I can also get a damping matrix by fitting a proportional damping model from the experimental result. And now this K and M matrix, once we do a finite element analysis, is going to be huge. It's going to be say 1000 by 1000 or even more these days. So, we cannot afford to do analytical model expansion theorem, the things that we have learned earlier. Though I have just talked about the benefits of doing that, before doing a full scale analysis, we always do a simplified analysis of the system to understand the system. Now, so I will not talk about finite element method, that is an entirely different course. There are several good textbook and courses available on finite element modeling to solve a dynamics or vibration problem. What I am going to talk about in the next few slides is about the numerical time integration. So, let me move on to it. So, if I look into the equation of motion that I would get, okay, either through from the free body diagram using D'Alembert's principle, I will get the m, k, and I can always get the C matrix. I know the force applied, so I get this equation of motion. So, this equation of motion earlier we have solved by taking u as modal matrix phi into eta, and then we have solved it. But as I said, this is not possible for a large system. For a large system, we try to solve this numerically, and there comes the understanding of numerical time integration. So, the best reference according to me to the book that I am going to follow on this is Finite Element Procedure by K.J. Bathi. So, there is a particular chapter on numerical time integration for dynamics problem using finite element method. There the techniques that I am going to talk about next are explained in a very detailed way. So, now let us look into the system. So, if I look into this equation of motion as well as the equation of motion for a single degree of freedom system is nothing but a second order ordinary differential equation. All of us appreciate that, second order ordinary differential equation. So, we all know how to numerically solve a OD. There are several techniques, several numerical techniques available to numerically solve an OD. MATLAB has this inbuilt codes, inbuilt toolbox which are called OD, OD23, OD 4-5, which can directly solve this kind of equations. Now, how do they solve this? In that case, we do not get ut as a continuous, we do not get ut as a continuous function of time. Instead, what we do is an Ft, the force, is also not known. This is also not known as a continuous function of time. Instead of that, what I know is that I know f as a discrete function. So, f is going to be, so of course, f is n cross 1, u is n cross 1, k is n cross n, so on. So, of course, f is n cross 1, a vector with length n. Now, so let me write this as f1t, f2t and so on till fnt. So, what is Fn? Fn is the force acting on the in the direction of the nth degree of freedom. F1 is the force acting in the direction of the first degree of freedom. Now, all this while we have been knowing F1, F2 and so on till Fn as a continuous function of time. Now, when we are trying to solve this as an ordinary differential equation numerically using numerical codes or using ODE solver, what I need to know is that I need to know each of this force F1 as F1 T1, F1 T2 and so on till F1 T n, and so on. I need to know Fn T1 to Fn T2 to Fn Tn. So, I will have a discrete value of force. So, the force is going to be known at discrete time instance T I. Okay. So, in other words, I will know F1 T I, where I is going to be 1 to m, and F1 comma P comma m, and F1 Tp is going to be T naught plus del T into P, and where F1 T1 is equal to T naught. Okay. So, once I obtain my force in this discrete form or at a certain time instance, then I will, if this is the force that I have, then my response is also going to be U1 T1, U1 Ti, U2 Ti, and so on till Un Ti, where I is going to be 1 to m, right. So, now this is the very commonly used ODE solver that can solve this system. But when we are applying this kind of ODE, numerical ODE solver, we should know certain things about a ODE solver. The first thing that we need to know is that any numerical time integration scheme. So, we will call this as numerical, these are usually conventionally called as numerical time integration scheme. So, numerical time integration schemes are of two types: direct time integration scheme and indirect time integration scheme. So, we are going to talk about this in detail in the next lecture. Thank you.